Here's a short Matlab demo of the existence of Nash equilibrium. Now here is the function g sub I. So it's different for each agent. So what are the arguments of the function g here? First, you have to specify the index of the agent, whether it's agent 1 or agent 2. And then you have to specify the pure action of that agent 0, 1 or 1, 0. And then you have uh, this argument S sub I, which is the mixed strategy of agent 1, and S2, the mixed strategy of agent 2, and then U is a payoff matrix. This payoff matrix must match that of the agent you specified and the action. So this agent, this action, and this payoff matrix must all belong to the same agent, and the output is the value of g sub I, that's this here. Now this is the function f. F takes in two arguments, which are the mixed strategies of agent I and agent negative I. Here we have two agents, so S1 and S2, you have to specify the two mixed strategies of agent 1 and agent 2, and this returns another mixed strategy, pair of mixed strategies rather. It's S prime I, S prime negative I. And here in the function, you also have to pass the two payoff matrices for agent 1 and agent 2, which are P and Q. And this code it's mostly graphics. It shows the bimatrix game between the two agents along with their payoff functions. This here is the output of that previous function. This is what it shows. This is the agent 1, this is agent 2, this is x, 1 minus x, y, 1 minus y. Remember that this vertical line is y equals 1, this is y equals 0, this horizontal line is x equals 1, and this horizontal line is x equals 0. So at this point, x and y are both 1. Likewise, at this point, x and y are both zeros. This is the point where x equals 1 and y equals 0. This is the point where x equals 0 and y equals 1. This function I call Nash grid, and it produces a mesh plot that you shall see next. I could have implemented this using mesh grid and quiver, which are two standard MATLAB commands. I just chose to implement the function this way. And the output of this is next. So this is the mesh plot that is produced by that function. Now, you see that you have tiny lines here, which begin with a red dot. That red dot here corresponds to the argument S1, S2, the mixed strategies of agent 1 and agent 2. And then the blue line here points along the direction of S prime 1 and S prime 2, which are the outputs of this function here. Note that I'm not drawing the entire line all the way to S prime 1, S prime 2, because then the lines, it turned out that the lines would have been really long. And so for visual clarity, I just chose a small fraction of the whole line. I just go 10% along that direction actually. So what this shows is for each red dot, what's the direction for the joint strategies to move to yield better payoffs according to this function f. This is the same function's output for another set of payoffs. example 2. And you'll see that from these lines, you can see that the Nash equilibrium is somewhere here. This is a third example which has a pure Nash equilibrium at the point uh, x equals 1 and y equals 0 right here. And you can see all the blue lines are directed towards the pure Nash equilibrium. Coming back to the first example, the way these blue lines are directed gives us an idea. Here's the Nash equilibrium, and suppose we start from some arbitrary joint strategy here, let's say, and then follow the directions of the blue lines, small steps at a time. Eventually, somehow, we will reach the Nash equilibrium. And that's what the next function does. Here is the function Nash Path, and it takes small steps along the blue lines that you saw earlier. And so you have to give it as arguments the payoff matrices and an initial starting point S0, which is x comma y. And next we'll see what this produces. Note that this is optimized for visual clarity, not for speed. So it takes a huge amount of time to compute. So with this as the starting point right here, if we follow the directions provided by these blue lines, we will eventually converge to the Nash equilibrium. The color of this line, the way I've coded it, changes gradually from red to green and to blue as it approaches the Nash equilibrium. Again, this is for visual appeal, nothing more. So this somewhere here is the Nash equilibrium. For another starting point, again, you see that it converges to the Nash equilibrium. And this is for another starting point and yet another starting point. And this is example 1. If we change the payoff matrices, then the Nash equilibrium point changes. So this is example 2, and this is where our trajectory converges to. Somewhere here is the Nash equilibrium. Now, example 3 had a pure Nash equilibrium, and so if we start anywhere, you can see it converges pretty quickly to the Nash equilibrium here.